the title of this talk is Hardware-Based Acceleration of Homomorphic Encryption, and I'll go in detail through every word of the title. But first, I wanted to say a few things about the status of data protection today, because data appears in different forms. Data appears in transit, end-to-end points. So when you connect to the internet, you talk to a service provider. This communication between you and the service provider is encrypted. You see now everybody's looking for this lock in HTTPS. That data gets encrypted before leaving your computer, is transmitted over the internet encrypted, and then is decrypted at the end in order to be processed. So data in transit is kind of an okay status, right? Of course, there are issues there too, but generally we have some good solutions for data in transit. Data at rest, this is when our data resides in our hard disks or flash drives. Now, many modern hard drives, they have hardware, and they have encryption at the hardware level, or you can do software encryption like BitLocker, that things are encrypted before they're stored. So we're also trying to address the data at rest problem. What happens to the data when they're not used and they're stored in non-volatile memory. But what is a problem, and this talk is about that, is data in use, right? What happens when we actually want to use the data? So when we move it around on when we store it, we have some ways currently that we can enhance security, right? But when we have to use the data, we have to decrypt the data, right? We cannot use it without decryption. So currently, any operational data, you have to decrypt them and use them. And once you decrypt, there are ways you can actually leak that data, right? And many of these you saw in this talk, in this seminar, you'll see more tomorrow as well. But there are many ways data can leak when the data has to be used. And data is used in what we call the endpoint, right? That when the data is moved around the internet, it goes somewhere to be processed, and we call that the endpoint. And the endpoint may be in the cloud. So you send your data to a cloud service. The service may be curious. They may want to look in your data in order to sell you a service, right? To gain something financially. Or the host could be malicious. They may try to look in your data for more nefarious purposes. So these are the two things I mentioned, that once your data is decrypted, the host of the data, if it's in the cloud, can maybe look at it and try to use it to towards some goal that you don't agree to or you're not aware of. But there's also the case that we have on our own computers, right? And our own computers also have vulnerabilities across the stack. At the hardware level, we've seen microarchitecture leakage with Spectre and Meltdown and other attacks. There's research on hardware Trojans, even though there are not many documented cases on that. Still, the hardware leaks, as we also saw in the previous talk with side channels. The operating system has vulnerabilities. It has some bugs that can be exploited. And also the application itself has bugs, and it could have intentional backdoors as well. So even if we have our own computer, there's no guarantee that the data is safe, because our computational stack is insecure throughout, from the hardware to the operating system to the application itself. So the conclusion, what I'm trying to conclude here is that the endpoints cannot be trusted, right? Once the data is decrypted to be processed, then there are many ways that data can leak. So this is a problem that's known, and there are many approaches towards solving it. And different problems assume different threat models, but I classify them in two big categories. One is using hardware enforcement, like an enclave, like Intel SGX and ARM Trust Zone, and there are academic solutions that appear a lot, Sanctum, Ascent, Cherry, and so on and so forth. But these, you have to change your current hardware or add to your current hardware in order to create some hardware enforcement. The other solutions are more on the crypto side, either purely cryptography or protocol-based, like secure multi-party computation. Homomorphic encryption is the one I'll focus on in this talk, functional encryption, and more. So you can classify them in two with pros and cons, either hardware side or crypto side. So what I'm discussing in this talk is, because the problem starts whenever we decrypt the data, How about we never decrypt the data, right? If you never decrypt the data and you still use it as is, then you get some kind of a blanket protection, right? If you have a backdoor in your hardware, a Trojan, if you have a problem in your operating system, your data is encrypted. So even if it leaks, it looks like random data. So the capability of processing data where the data stays encrypted is enabled by a special form of encryption called homomorphic encryption. Again, homomorphic encryption is a special type of encryption that allows meaningful manipulation of data without decrypting the data. And to give you a very basic example, let's say you have two numbers, 5 and 7. You would encrypt them with a public key, and then you have now two ciphertexts, right? You have the encrypted counterparts. These encryptions, this ciphertext, can be processed without decryption. So there's some kind of a manipulation you can do that produces a result, that this result is not understood unless you have the key to decrypt. But when you decrypt, it will correspond to an operation, to an algebraic operation in the plaintext domain. So in this example that I'm showing here, I'm not sure if you can see my mouse, this operation in the box can be done in an endpoint that you don't trust. So the endpoint manipulated the data, but the endpoint had the result that it could not decrypt. So this 49 could not be understood by the endpoint. So this result goes back to the client, and the client only has the private key that can decrypt and see the final result. So this gives you some kind of a better protection that whatever bugs are in the endpoint or malicious or curious hosts, there's nothing they can do because they cannot see the end result. It has to be decrypted to be seen. And the key is not with the endpoint. So in this way, if you leak data, you cannot distinguish them from random data. So homomorphic encryption has applications. It's a newer technology. It's not newer, but its applicability is it's newer. Homomorphic encryption existed from many years back, but nowadays we see both more need for it and also implementations and implementations that are faster and more practical. One thing I mentioned, for example, in smart grid, right? You can aggregate data from different smart meters without compromising the privacy of the individual consumers. You can get, analytics about the power grid, what these users of the community, of the city, of a state, but you don't leak what each one is doing. You aggregate the data. You can do, for example, business analytics or genomics. DNA is sensitive, but you still want to process it, right? What is the trade-off here? You can encrypt it, process it, and get a result that only you know. So there are a few applications that currently appear for homomorphic encryption, and I'll explain one in more detail later in this talk. I did mention a few other examples, like multi-part computation, SGX. I wanted to emphasize with this slide is that these are not exactly competing techniques. Sometimes they can be complementary, or one has to be used depending on threat model in your application. You have to use one or the other. But the big difference is that multi-party computation, it's network bound, so assumes communication between parties, and it also assumes that there's no collusion between parties, right? And it's interactive. The homomorphic encryption is more of a fire and forget, right? You send it to the cloud, you forget about it, you get the result back, you decrypt, you see the result. There's no interaction needed between the parties. You have your data somewhere else, you leave it there, you only get back whatever you need, whenever you need it. SGX gives you an enclave, but the path Intel took to do security by obscurity with SGX, by not revealing details, people found ways to leak information through SGX. It has known attacks. So it's not at a state that it gives strong cryptographic guarantees currently. All right, so homomorphic encryption, as I said, it manipulates encrypted data, right? And this is magic to an extent, but behind magic, there's typically mathematics. So there's specific asymmetric encryption algorithm that the construction allows these operations to happen on ciphertext. And this one-to-one mapping is actually where the term homomorphic counts, that the operation in the plaintext has homomorphism to the operation in the ciphertext. A very simple example is parallel encryption. You start with 2 big prime numbers, and then to encrypt a message, actually the message appears in the exponent here and is the public key to an extent, and you have also some randomness for semantic security. So in this, when you encrypt the message with some randomness and you encrypt another message, we can observe that when we are multiplying the ciphertexts, you can see that because you have a common base here, the result ciphertext is actually adding the messages. So if I multiply the encryption of M1 to the encryption of M2, the result will be the addition of M1 and M2, because here this is the exponent. So you multiply something with the same base, then you have addition of the exponent. So that's an example of homomorphic encryption. So see here, I manipulated the messages without decryption by directly multiplying the ciphertext. Because the resulting operation, the plain text was addition, this encryption is called additive homomorphic. Multiplicative, for example, would result in multiplication of the plain text, and RSA actually, the vanilla RSA is without padding, is multiplicative homomorphic. So partially homomorphic, so different types of homomorphic encryption. What I just said is called also partially homomorphic. Why partially? Because it allows only one type of operation, unlimited number of times. So the only one type makes it partially homomorphic. You allow only addition or only multiplication. As you can understand, this puts constraints in the types of algorithms you can support, right? You cannot support many algorithms that only do addition. Of course, the many very interesting use cases, such as aggregation of data for a smart grid or e-voting, that also relies on aggregation of data. After partial, there's somewhat homomorphic encryption, where you allow some types of operations for a limited number of times. For example, you can have unlimited additions or one multiplication, or you can have many additions but some multiplication. So if you know your computation in advance, for example, machine learning, if you want to have an inference, you know exactly the computational path on the inference. So you can prepare your crypto system to support one inference of in your machine learning model. So if you allow some limitations in the number of times you apply the operation, then this is somewhat homomorphic. And then the most unrestricted one is fully homomorphic. It's the last one that allows some types of operations for an unlimited number of times. So fully homomorphic is the all-encompassing that you can do all applications. Well, all applications can be represented by a circuit. And the current schemes we have for fully homomorphic assume the existence of bootstrapping, because fully homomorphic has noise. The more you multiply, the more noise is being generated. And to clear the noise, you have to bootstrap. That it's a slow process. So currently we see more applications on the somewhat homomorphic side that kind of puts a bound in the computation you expect to have in the field. Challenges of homomorphic encryption, of course, is its performance. One operation in plain text becomes much slower if you apply homomorphic encryption to it. The exact decryptation is application dependent on the type and the depth of computation. Additions are faster than multiplications, and the more the depth, the slower your computation becomes, and it reaches a point that it needs bootstrapping or you have to stop computing. The other challenge is usability and applicability, because when you process encrypted data, you cannot see them. You cannot do certain things. For example, you cannot branch on encrypted data, right? Because you don't know if something is true or false. So you have your algorithm has to be constant time, or it has to be data oblivious, right? It should not depend on the incoming data for its execution. And that is not straightforward. It may not be supported by the exact application that you want to develop. So developing it with homomorphic encryption in mind is kind of a challenging endeavor currently. Also, the final result is encrypted. So it can only be, so only the private key holder can decrypt, and this could create problems in the interaction between parties. So these are the major challenges of homomorphic encryption. I mentioned performance degradation. It is application dependent. I have some rough numbers here, but the only thing you need to know is homomorphic encryption incurs orders of magnitude slow down. It's becoming much slower. It could be a million times slower, depending on the application, right? Nowadays, we've reached practical times, but again, for specific applications with specific models that many of them kind of become partial homomorphic, and you do very few multiplications. All right. So in the first part, I'm motivated what is homomorphic encryption, right? In the second, I'll focus on how to solve the problem of performance. And what we do, what I do at NYU in Abu Dhabi, we try to develop hardware for accelerating homomorphic encryption. And I have two sections. One is partial homomorphic, and the second will be fully homomorphic. So for partial homomorphic, we have built the processor. We called it COPHEE because we like coffee a lot. It stands for coprocessor for partial homomorphic computation. We presented at Host 2 years ago. We fabricated this in global foundries with the small design is 9 millimeter square. But what is unique about this chip is it supports very big data paths. And it supports up to 2000-bit data paths. And these are numbers that are used in partial homomorphic encryption, are needed for the operands in that form of encryption. Also serves by hardware of trust, and the operations needed for homomorphic for this type of homomorphic encryption is modular multiplication, modular exponentiation, modular inversion, and the greatest common divisor, which are more exotic units that don't typically appear in ASIC. When you want to have a modular multiplication, you do it with software support. You don't have a modular multiplier in your standard processor. Very briefly, this is what the design looks like. Most of the design, the biggest part was the GCD, the greatest common divisor, that is used for the modular inversion that we needed. There's modular multiplication, and the modular exponentiation also is spread out, and there's some other configuration registers. We also added a true random number generator in order to get the randomness needed for semantic security for our homomorphic encryption support. In terms of performance, what this chip does, we compared it to x86, and what we saw if you just use your Intel processor, because also the Intel processor can emulate the homomorphic encryption operations. Remember that, for partial homomorphic, you need mostly modular operations, modular multiplication of big operands, 2000-bit operands, modular exponentiation that can be done with DMP, for example, in x86. But they're slower because an x86 has a native 64-bit data path. So if with our chip that is much smaller, we observed 2 orders of magnitude acceleration, and it also ran in a much lower frequency. That was the limit we had because of the IO pads. This can run much faster, but this is what we fabricated, and this already was 100 times faster and has potential to become much faster. So one way to solve the problem of performance of homomorphic encryption is hardware support. But for partial homomorphic, it may be restrictive in a way that only allows additions or multiplications, but there are very interesting applications that can take place. I already mentioned e-voting, and I also mentioned smart grid aggregation. But another thing we showed, and we participated in ITAS competition, a privacy competition in bioinformatics, we also saw how you can do genotype imputation using partial homomorphic encryption. So very quickly, genotype imputation is, when you want to sequence your DNA and get some results about, you may have some predispositions to diseases, for example, cancer. There's some correlations in your DNA, right? So when you sequence, it's actually very expensive to sequence your whole DNA. What you can do instead is you can sequence part of it, and you can fill in the blanks by exploiting correlations between SNPs, the SNPs that I have on the slides. So for example, if you have this as 2 and 0, this is most probably 1. So there are correlations that exist in our DNA. So when we sequence the DNA, we don't have to sequence all of it. We can fill in the gaps, the blanks, with correlation information. And this is actually called imputation. But as you know, when we sequence our DNA, we want it to be private, right? So the imputation service, in a way, will have access to our DNA in order to do the imputation, to fill in the blanks, as I said. So this imputation model uses the reference genome in order to fill in the missing SNPs. So we want to protect that, right? Because if our DNA leaks, then, for example, this can be used by our health insurance to increase our premiums if they discover we may have predisposition to cancer, and we will require more expensive treatment in the future. So there's a privacy issue. And we developed some solutions with partial homomorphic encryption that allows you to run machine learning it actually became a linear model, right? And this is the trick when you do machine learning, that partial homomorphic allows additions of ciphertext, but that still allows you to do multiplication with plain text coefficients. So if the model is public, then you can actually do some, not the training, but the inference can be done fully in homomorphic encryption. And that's what many papers are doing currently, CryptoNets and others. So we showed some application of partial homomorphic. Partial homomorphic is one type of encryption. We have already some hardware to accelerate it, but now we're focusing on accelerating fully homomorphic, because the fully version of homomorphic encryption is way more powerful and allows most algorithms to be expressed in that. So we're trying to build something. This is currently something in progress. In partial homomorphic, the hardness assumptions are 2: factorization, similar to RSA, and this DCRA, decisional composite residuosity assumption that the Palier cryptosystem is using. With these problems, security comes with keys that are, of course, as always, a size and above, right? So with these problems, with 128-bit, we need more than 2,000 bits. Currently, we're at 3,000-bit keys. So we managed to build that chip, right? But for fully homomorphic, there's a different hardness assumption. And this is called the main one that's used, ring learning with errors, which is the learning with errors problem specialized to polynomial rings. So this ring learning with errors, actually, this learning with errors is also used in post-quantum cryptography. So these FHE schemes are also considered for now post-quantum schemes as well. But this problem, when you actually you convert, when you encrypt, you encode and encrypt your plain text, you create a polynomial, and then the degree of the polynomial and the size of the coefficient are related to your security levels. So and there is a connection between the two. How big is your polynomial degree, and how big is your coefficient size? How many bits is one coefficient in your polynomial? So these two are related, and the relation is creating a security level. So the more, and within the security level, the polynomial degree and the coefficient, you have your noise budget, right? Remember I said before, the more you compute with full homomorphic, the more noisy the ciphertext becomes. So it can allow up to some noise, but if you have a bigger polynomial, it will allow more noise, but it will be slower to process. So there's a very interesting trade-off to be discovered in the algorithms when you try to support it with homomorphic encryption. So because you have such big polynomials, the degrees start from 4,000, but it's not uncommon to see 16 or 32,000 degree polynomials. And the number of bits, as you saw in the table before, can go up to 800 bits, right, or 1,000 bit coefficients. CryptoNets, a paper from Microsoft a few years back, they used smaller numbers to prove that machine learning can be done with smaller numbers too. They used a 4,000 degree polynomial that's pretty small with 110 bits ciphertext, but even that's very small in terms of noise budget polynomial, made one bit become 55 kilobytes. So this expansion is tremendous between the plain text to ciphertext. That's why it's much slower to operate on. So the hardware has to support high degree polynomial multiplication. That's not easy to support and typically becomes a big entity engine. And we also need to support large word size multiplication that has our non-native size above 64 bits, maybe up to 1,000-bit multiplications. So we have something that we're building already. We call it COPHEE with an F. It has big memory and big multipliers, and a unit that tries to balance things between the two. And we're currently trying to fabricate that. At the same time, we just got a grant from DARPA because there's the DePRIVE program that they have set a very ambitious goal. This is what I said before, right? With today's CPU unencrypted, something that is done in an hour, it will take a year with a full homomorphic. So what DARPA is trying to achieve is up to 10x degradation in performance, which is a very ambitious goal. And we'll participate in the program and we'll try to make this happen. To conclude, so I can allow some time for questions. How far are we? Performance is still a problem with homomorphic encryption, with full homomorphic, partial not that much. Fully homomorphic, we're trying with ASIC. Some people are trying with GPUs. Domain-specific architecture, there are things we can do. Applicability is a problem. What application can be supported and how. It's not easy for someone to program in homomorphic encryption. And usability I mentioned. Many things I've said are available as open source. The code for the coprocessor, the RTL is available online. The benchmark we use for measuring homomorphic encryption are available online. And we have our own compiler for homomorphic encryption. Also, you can find in the lab's webpage. And with that, I conclude my talk.
Okay, thank you very much, Michail. It was very interesting. I mean, we are relatively close to each other, but I guess that there are lots of things that we work on together that we have synergies on. So there are a few questions. We have only a couple of minutes left, so we can start for the first one. And if we don't have time, then it would be great if then you could answer also offline by typing the answer. So the first one says, what about correctness? How would you get it?
That's an excellent question, right? The blessing and the curse of homomorphic encryption it's malleability. The fact that you can change the ciphertext is a problem. You have to correctness, you have to pair it with other techniques in order to ensure correctness. Currently, you have to accept the malleability and add signatures, add MAC, find another way to add to ensure correctness of your computation. Currently, homomorphic encryption suffers from that problem.
Okay, thank you. There is an additional question. Maybe we have time. There's still a minute left. So Xiaojie is asking, in machine learning, we may need floating point. How can we apply hardware-based homomorphic encryption to tackle the floating point efficiently?
The hardware is unrelated, right? So I would rephrase the question, how do you apply homomorphic encryption with floating point? And the question comes with its conversion to fixed point. So floating point assumes a scientific notation that you have the exponent, the mantissa, but you can also represent decimals with fixed point. It's like a big integer with a dot that is in a fixed position. So when you want to support floating point, you convert it to fixed point and use fixed point arithmetic in your programs, same way you would use integer arithmetic.
Thank you very much, Michail.
Thank you,
it was a pleasure having you presenting this interesting work.